Okay, so we're getting on to one of my favorite subjects, dispersion and colloidal stability. I gave a little presentation on Wednesday, and I asked who works on ceramics, and people were very shy, but I mean, I work on ceramics, so who works on ceramics? Huh? Okay, so people are getting less shy as the week goes on. So who works with nanopowders? Well, we have a nice audience today. So who doesn't have problems with dispersion? Okay, so let's see if I can convince you that what we've been doing over the past 4 years in Nanoker, and particularly Uli's computational skills, has given us a little tool to help us perhaps get towards, the easiest way to dispersion. This is the title that we like to use when we're presenting this. It's a little bit longer than, So a user-friendly program for interparticle interaction energy calculations, Hamaker, the first step in successful nano-sized powder dispersion. I think I've convinced you, and I hope that you're convinced. If you have aggregated powders, you have to admit it and you have to solve the problem. Otherwise, you're wasting time sintering and characterizing, huh? And I've seen too much of this over the past 10 years. It's such a shame, huh? Have a little bit of patience. Stay with the first steps, huh? You need sometimes 6 months, huh, to work out how to disperse and characterize properly stage 1. The rest is much easier afterwards. Okay. We know why introduction we've sort of already done. Colloidal processing. Why are interparticle forces important? We've seen all that through the week, huh? Control of microstructure, particle packing, we've seen that. I discussed that on Wednesday. Nano-sized powders form aggregates. So I'm not going to go through those things now. I'll move straight on to interparticle forces and colloidal dispersions and give you a little theoretical input so then you can see what we need to do afterwards. I'll go through the Hamaker software in its first version, give you a highlight of the second version with its improvements. Huh? I'll give you an example of how these type of things can be used for nanoceramic processing, which is now an industrial product. And if we got time, I'll show you the program live. We can manipulate a few parameters. As you all know, these type of things are very dangerous to do in public, but we'll see. We should have time. We're not running behind time yet. Huh? So, interparticle forces. This is the slide that I used on Wednesday. Huh? So, we have attractive dispersion of van der Waals forces, which are a function of the material's dielectric properties and the geometry. Huh? So we have repulsive forces, which would be electrostatic from ion adsorption, dissociation of groups on surface. If we adsorb a polyelectrolyte, we can get charged polymers. Huh? So we can have our electrostatic repulsive force. We can also use the steric. If we adsorb a polymer, we have the steric repulsion, where h is always the distance between the particle surfaces. Huh? So the attractive forces. Huh? So we have our particles here. We have particles of identical size. They're simulated as spheres. Distance between the surface is h. Huh? So van der Waals forces are always attractive between particles of the same nature. They result from the fluctuation of dipole moment in one particle that induce a correlated response in a nearby particle. Okay? These can be permanent or induced. They can be instantaneous, that is the London or dispersion forces. Huh? And they're a function of the material's dielectric properties and the geometry of the situation. Okay? Hamaker took a simple approach at the beginning of the last century. He said, we'll just sum all the interaction energies of all the molecular species in the particles. Huh? So a simple summation, which obviously is quite huge. So we end up having interaction potential, which is a function of the Hamaker constant, and geometric factor, where h is the distance between the surface of the particles and the particle geometry. The Hamaker constant, like I say, it's attractive between similar materials. Leonard Bergstrom showed very elegantly if you take dissimilar materials like silica and silicon nitride, you can actually create a repulsive force. So between similar materials, if you have a multi-phase system, you have to think a little bit. Dielectric properties of both the material and the liquid in between or the gas in between. So if we're in suspension, the static term of these interactions can be screened if we have a high concentration of electrolyte. Like when we make cement, we disperse particles, there's dissolution. We're working in 0.4 molar solution. So electromagnetic sort of transport in this medium is different than if we're in 10 to the minus 3 moles KNO3. Retardation can also be considered. This is when there's a loss of correlation between the dipole fluctuations. If the particles get too far apart, then we start losing the correlation and the attractive force diminishes. At short separations, that is 30 nanometers between the particle surfaces, we can use this simplification where now we have particles of a different size. So we have the harmonic average radius, which is this formula here, and our attractive force depends on the Hamaker constant, the distance between the surface, and the different sizes. The Hamaker constant itself, like I said, depends on dielectric properties. That is the polarizability of this material. And also the medium that separates it, be it air, vacuum, or a liquid. Valid over the whole range of electromagnetic spectral domain. For particles of the same size and same chemical phase in vacuum, we can make this type of calculation. So the Hamaker constant, we can calculate from the number of molecules per unit volume, its polarizability. These are the imaginary electromagnetic frequency. This is just mathematical. It allows the evaluation of discrete, equally spaced imaginary frequencies. It makes it easier to actually calculate the Hamaker constant. Here are examples of magnitude for alumina in water and in vacuum. And you can see there's a significant change. So particles, when they're dry or when they're in suspension, there are different forces between these particles. So you need, and if the attractive force and they're in a potential well, you need to kick them out with some energy. So the attractive force depends on this Hamaker constant. One good source is Leonard Bergstrom's review. One day we'll get a little list up in our Hamaker program, but for the moment, if you don't know what to do, look in this source, and then if you don't know what to do, send me an email. Okay. Like I said, we talked a little bit about retardation. There's also this possible phase shift between dipoles because of many body effects, screening in the presence of high concentration. You notice that I didn't even notice that this slide is in French. I mean, there's a little bit of French from time to time. I don't know, I have slides in French and English, and sometimes I don't really notice the difference anymore. I hope my Spanish gets like that one day. Anyway, so H is this form factor, and we have something, if we have parallel plates, it's quite simple. If we have identical spheres, it's a little bit more complex. If we have different size spheres, then we have to do a few more calculations with current. I mean, in the 1950s, this was a little bit of a nightmare, but in 2009, this is trivial with our modern computers. So that's the van der Waals forces. The attractive forces depends on the dielectric properties of your medium. Okay? Electrostatic force depends on the surface charge density. We can have dissociated groups or adsorbed ions. We can have adsorbed polyelectrolytes like polyacrylic acid, which is the main component that Darwin see, our classic ceramic dispersant. So basically, we have the electrical double layer. We use a Poisson-Boltzmann and the Bi-Haeckel theory to describe the ion distribution in solution near a charged interface. Normally in simple ionic medium. So basically, what we've got then is this electrostatic force. So this is represented here, where we have the electrostatic potential. That's the surface potential, which we can derive from the measure of a zeta potential. And, oops, sorry, go back up. And here we have information. Kappa is the reciprocal of the electrical double layer thickness, and H is the distance between the particles surfaces. And again, you see that this is dependent on our harmonic average radius if we have particles of a different size. So the electrical double layer, just to remind people, we have a surface that has a certain charge. I mean, it's negative, positive ions come to reduce this free energy of the system. As we move away from the surface, we get less and less positive ions. Here we have a layer which is quite strongly attached. We have a second layer where it's more diffuse. We have some other ions. And finally, when we're out into the bulk, we have the bulk concentration distribution of ions as expected. So we have our 1 upon kappa, where our surface potential drops by 1 upon epsilon, 1 upon E. This is called the Debye-Skrelin length, or sometimes the electrical double layer thickness, kappa minus 1, which then depends on the ionic concentration, inversely on the ionic concentration, the effect, the permittivity, dielectric constant of our medium, vacuum, and the valence of the ionic species that are in solution. So we can calculate this. Sometimes the first layer is treated as a simple capacitance, and then we have our exponential decay from the Poisson-Boltzmann and the Debye-Huckel theory. So we have our electrical double layer, which sets up. The repulsive force is felt when these double layers overlap. Okay, so it's not like in your undergraduate physics lessons. The electrostatic repulsion is not the same between point charges in a vacuum. Okay, this repulsion is because of the overlap of these layers. The layers, the composition and extent of the layer depends on the surface potential of your material. So if you have alumina at pH 4, we have a positive potential, zeta potential of about 50 millivolts. We have a surface potential which is a bit higher. Yeah? And it's the distribution of ions at this charged surface which are then fixed. Yeah? And as we come in, we have this increasing concentration of species, yeah, of ions in solution. They lose when we start concentrating. So it's a little bit like an osmotic pressure. So if we have solution in, away from the particles, which is lower concentration, we have high concentration at the surface, we try and dilute that, like an osmotic pressure, and this pushes the particles apart. So it's not a direct classic physics vacuum electrostatic interaction, but it is dependent on the surface charge. So the double layer thickness, which affects both the effective size of a particle. So if you're talking about nanoparticles and this layer is thick, so if we are in 10 to the minus 1 moles, we have we have this double layer which is 10 nanometers thick. We have a 10 nanometer particle in diameter. We have a 10 nanometer thick layer. Its effective diameter is 30 nanometers. So then you have problems making high solid weights or high volume concentrations of your nanoparticles. So for nanoparticles, this double layer is really important. As we go up in concentration, you can see if we're now at 0.1 moles, the double layer is only 1 nanometer thick. So we start feeling the repulsion only at 1 nanometer, where the attractive van der Waals forces are quite strong. So the ionic composition of your material, of your solution, is really important with respect to these forces. If we change the electrolyte, so if we go to something like calcium sulfate rather than sodium chloride as your ionic medium, then you can see that as the valence goes up, we have an increased effect, and we have thinner effective double layers. So, like, I've done a lot of work on cement, which is quite complex, because normally in ceramic processing, we're normally working with relatively simple electrolytes. Cement is quite complex. There are 7 different species. So then you have to work out an equivalent electrolyte. But we've done this in Robert Flatt's thesis, and we managed to fit the data with a numerical Debye-Huckel expression, and in fact we can use a non-integer value. So if you have different types of species, if you have 2+, 3+, and 1+, you can actually take a non-integer value to represent this in your calculation. Just to show that this sort of thing, these are models. So one of the first questions, okay, so two of the first 4 questions after the general introduction was, are they valid? Yeah? So this is a nice example of showing how this electrostatic repulsion between 2 charged plates. So these are mica plates made on the atomic force system, where we have 2 curved surfaces of mica. They come together, and then you can measure the force. This is classic work done by Izriatshvili in the early, it comes from his book in the early 90s. The work was done in the late 80s. And as you can see, the experimental points are the dots, and these are the two theoretical lines, and you can see up to a couple of nanometers, it works really well. So when you have a system where the geometry is well defined and the surface charge is well defined and your medium is well defined, this works very well up to this couple of nanometers layer. So if we now move on to steric repulsion, for steric repulsion, we have 3 important interactions. We have polymer-polymer, polymer-solvent, and polymer-particle. So we need the polymer and the solvent to have an affinity for both the solvent and the particle surface. So the choice is important. We need a certain degree of surface coverage. If it's too low, and if the polymer adsorbs on the surface, so he likes the particle surface, or she, it likes the particle surface, it comes together. But if it's not totally covered and the polymer is long enough, it can attach to 2 surfaces. So we get what we call bridge inflocculation. Also, the adsorption needs to be high enough. So if we have particles under high shear, so if we're mixing really in a high shear system, if we're doing injection molding or if we're high shear filter pressing, then the polymer needs to stay attached. We want it to carry on repulsing. So it needs to be attached high enough. It's very important that the polymer has a certain affinity for the solvent. It needs to be extended from the surface such that it can keep the particles apart. So another bit of French. So this is a cartoon from our famous Asterix series, which I'm sure everybody is aware of. And these guys are on their way to conquer Great Britain. And as you know, in Great Britain, you don't walk on the grass. So this guy is saying, hey, il faut pas marcher sous le gazon. No walking on the grass. Don't know why, because it rains so much in Great Britain, the grass is always in great shape. In Madrid, I can understand this. Anyway, these guys are coming. He's trying to stop them coming. So if he's going to stop this guy hitting him with his sword, his steric barrier has to be long enough to stop the other guy hitting him. Okay? So the key factor in steric stabilization is the adsorbed layer thickness. So this is what we have to control. So there's a great article by Pierre Degene. If you want to read about the basic approach to this type of scaling methods. So what we got here again is our harmonic radius for 2 particles of different size. This is our steric force. This is our adsorbed layer thickness. And we have other factors, the spacing of the adsorbed molecule on the surface. This is for a sphere-sphere geometry. Like I say, this all depend on geometry. So if you then look at, other approaches, like I said, this is a great article. It's geometry specific. This is now for a plate sphere or a brush conformation. Very difficult to find out. Sometimes you can use AFM to find out how your polymer is adsorbed, what type of conformation you may have. Huh? But again, it's always the same parameters. Huh? And like I said, there's just this S factor, which is the distance between the contact points of polymers on the surface. Huh? So you have this effective adsorbed layer thickness, and these are the parameters you need if you're going to model these type of interactions. Huh? So a little example with polyacrylic acid. Huh? So we've used AFM in another European project called Superplast to estimate the extension. This is an example of polyacrylic acid. We see here it has this carboxylate group at pHs greater than 6. These are dissociated. The isoelectric point for alumina, where the zeta potential is 0. So at pHs below the isoelectric point, we have a positive surface. For pHs above the isoelectric point, we have negative surfaces. Okay? So what we've got is, if we at pH 10, the polyacrylic acid is totally dissociated. Huh? So we have a negative polymer, so it doesn't like itself too much. It's quite extended. There's charge all the way along the backbone, so it tends to have an extended conformation. The surface is only slightly negative. Huh? There are still sites whereby it adsorbs. It adsorbs strongly. It's very difficult to desorb. It's more or less irreversible. But because we have a negative surface, a negative polymer, it adsorbs in what Dejean described as the brush-like fashion. Yeah? We have pH 8. Now we have a surface that's slightly positive. The polymer is still highly negative, but we have a few more points where it can attach on the surface. So we have something that's called, it's called the mushroom configuration. And the mushroom configuration means that the density of polymer segments is slightly higher away from the surface than at the surface itself. So if you plot the density on an axis, you see that the density is low at the beginning and increases as you move away from the surface. So you have a higher density of polymer segments at a certain distance from the surface. The pancake or flat, you can see Dejean was French, huh? With his gastronomic description of how polymers adsorb on a surface. So flat as a pancake. So here we have the situation where the surface is highly positive, the polyacrylic acid is still negative, we still dissociated a certain percentage of the groups, and so we can attach at many points, and we have this flat effective adsorption. At pH 2, polyacrylic acid does not like water. Huh? It's not dissociated, it really does not like water. So you form these blobs. Huh? You form a very tight polymer blob. We still have a highly positive surface. In fact, here you adsorb 10 times more, or you can adsorb. Depends if you put enough polymer in the solution. You adsorb 10 times as much polymer as here. But this is not at all stable, because the polymer doesn't like the solution. Huh? It doesn't like the liquid. It adsorbs to the surface. It'd rather be at the interface than in water. If particles come together, the polymer-polymer interaction is much more preferable than polymer-water, so they just stick together. Yeah? So you're not only not dispersing it, even if you have an adsorbed layer, huh? I mean, the polymer still has to like the solvent. Which takes me on to pastis. Yeah. So who's never heard of pastis or ricard? Huh? Okay, no problem. It's an alcoholic beverage from France. I don't know, lots of countries have versions. There's Ouzo in Greece. Huh? So, it's based on aniseed, anethol. So this anethol molecule, huh? And the anethol molecule is you can see it's not very polar, huh? So it doesn't like water very much. So in this version of these alcohols, we have 45% alcohol. With 45% alcohol, the molecule remains in solution. Huh? So it's quite happy to be solvated. the manufacturers recommend you drink this with 2 parts pastis and 5 parts water, huh? So you put it in. I don't know, I like it. It's a little bit early for aperitif, but you know, it's a gorgeous taste. And also I'm quite thirsty after last night. So you can see it's gone cloudy, huh? We formed an emulsion. Anethol doesn't like it. There's too much water, not enough alcohol. It can't create a low energy interface, so it agglomerates, huh? So the key thing, and I mean also, you know, the French are really quite perfect when it comes to, you know, drinking and eating, huh? There's a group in France, Griot, that looked at, in fact, the rate of these grow, huh? So they're not stable. They want to create a minimum energy interface. So in fact, you see that they coalesce and create a lower and lower quantity of the unfavorable energetic interface. So what you got to do is you just take a little bit of soap, huh? You put it in. You have to create an interface that is favorable, huh, for our molecule. So steric stabilization is exactly the same thing, huh? You need something which will extend into the liquid and attach to the surface. Here we just have a little bit of soap, which is a polar head, a long organic tail, and we redisperse our anethol. Problem is, I can't drink it anymore, huh? So I'm going to remain sober until the end of the talk, huh? Okay. So that's my little, as we saw the other day, overall interaction energy, the LVO theory, we just use the algebraic sum of all these different forces, huh? So we have our attractive van der Waals, we have our electrostatic repulsion, and we have our polymer effective thickness repulsion, huh? And this gives us the total interaction force, which is a function of our particle size, okay? Quite important. And then we put them together, and if we're lucky, we end up with a repulsive potential, which then stops our particles from aggregating. And the big question is, what do we need? Yeah? So, like I said, Leonard Bergstrom did some very nice work back in the early 90s, got some nice qualitative results for alumina and fatty acids, so we know that the general approach works. Uli has created this program, which I'm going to show you in a moment, huh? Which we can then use to actually make these calculations, huh? One of the reasons why this work wasn't quantitative was because we don't take into account the particle size distribution. This is something I've been working on with Robert Flatt for a couple of years, and we've created at least a yield stress model for gels, huh? So if you have an attractive network, we've worked on taking into account the particle size distribution using an analytical model where we can predict the yield stress necessary to move. So if you're doing tape casting, you normally use something that's, I was going to say refluidifiant, so how do you say refluidifiant in English? Huh? So it's shear thinning, okay. Sometimes words come to me in French, and after 20 years of teaching in French, I mean, my English is a little bit bizarre. So you have shear thinning, huh? So when you're doing tape casting, you have the doctor blade, you have high shear, it's very fluid. Once it's past the doctor blade, you don't want this to run off the edge of the tape, you want it to have something, so under shear, we have something that's shear thinning. So with this type of model, you can work out sort of the shear necessary to make things flow. I won't go into detail today, but just to say that it's something we're trying to do to get more quantitative in our predictions with respect to reality, and it works quite well with 1 or 2 limitations. Okay, how can we use these, huh? So what we've got, people say, okay, I don't know, I mean, when I started working in sort of dispersing ceramics about 20 years ago, everybody said, okay, 30 millivolts is what you need to disperse a ceramic, okay? And this is something which quite a lot of people still use as a rule of thumb. But really, it's very, very difficult to know what you need, huh? So we have an effect of size, ionic concentration, charge, and adsorb layer, huh? So if you take the example of size, we have 10 to the minus 2 moles, 30 millivolts, we have alumina. Huh? So this is our zeta potential. If we have particles of 500 nanometers, we have a potential barrier of 30 kT. 250 nanometers, it's less. 50 nanometers, there's no barrier. Huh? So you can have these conditions. It can be good for some size particles, but not for others. Depends on the size. Ionic concentration. Huh? So if we take 250 nanometer particles, 30 millivolt surface or zeta potential, alumina, we're at 10 to the minus 3 moles, a 40 kT barrier, 10 to the minus 2 moles, only about 10 kT, 0.1 moles, no barrier. So it depends on the ionic medium. So if you're working with something where there's a risk of a certain amount of solubility, you can work at high pH or low pH to create high charge. Huh? But if you start dissolving species and you modify the ionic concentration, you have to be careful. We saw the little trick this morning that for making these disordered photonic crystals, what they did was they added salt. Huh? So they added salt to get rid of this electrostatic barrier. Huh? So then you can coagulate the particles. So also depends on charge. So if you have something that's 250 nanometers and 10 to the minus 2, minus 15 millivolts, no stability. 30, a little bit. 50, a massive barrier. Huh? So you have to manipulate these parameters. Adsorb layer, you can see immediately just by adsorbing for 250 nanometer particles for 20 millivolts, 10 to the minus 2, just 1 nanometer cuts out most of the attractive minimum. Yeah? So if you have an attractive minimum that's deep, then these things don't come out. Huh? You end up with a gel or hard agglomerates. If you're drying things, you have to go back in, you have to mill it to break them apart. If you put on a steric barrier, you get an attractive force. So these things will form a gel, but you can break them by ultrasonic treatment, huh? Or by like milling. So they break. So under shear, you can get that out, and then it'll go back in. Yeah? So it'll be reversible. So this is one way to actually control the rheological properties of your material. A 5 nanometer layer, it's stable, huh? It's long enough that we never feel the attractive van der Waals forces. So the program calculates for spherical particles, takes into account electrostatic, steric, and dispersion forces, also estimates the required barrier for a certain stability period for the formation of doublets. So it's not the total stability long term, but once you start forming doublets, everything else goes very quickly. So you get an idea of where you can start working. We think it's essential to have an idea of a processing window. If you need something to be stable for 1 hour or 24 hours, it's different. A 10% volume fraction or 40% volume fraction is different. The number of collisions are different. Huh? So it's been designed as a single window application. I'm going to show you Hamaker 1. It's still available on the website. Hamaker 2 is also available, but I'll go through Hamaker 1. It's a little bit simpler to present. You need a Java environment on your computer. The general parameters are particle radius. Hamaker 1 is only monodispersed particles, but you can look at different sizes to see the relative forces. But in Hamaker 2, you can now modify. In fact, you can look at different size particles. So we have temperature. We have the plot of the interaction potential as you see it, the 2 axes, and the number of data points. So the number of data points is just to get a smooth curve. If you have too many data points, then it's a little bit slow on your computer, but I've never had that problem, even on my relatively non-sophisticated computer. You can just plot less points. The attractive forces, we have the dielectric constant of particles in the liquid medium. They're also used in electrostatic calculations for the Begstrom model. We have a series of different models I'll show on the next slide. Refractive index, which is only used in the Begstrom model. Hamaker constant, like I said, if you have problems finding it, get in touch with us. We then we have, like I say, a series of attractive models. The explanation and the range of validity are in the accompanying document. So there's the program that you can download from the website, and then there's an accompanying document which explains where all the formulae come from, which range you can work in for the different models. If you have problems, get in touch. Basically, for the attractive, we have 4 models. We have a non-retarded, Gregory, Vincent, and Begstrom. The non-retarded is good for particles between 10 to 100 nanometers. Gregory is good for 1 micron. Vincent is very good for 10 nanometers. And Begstrom is the best overall. So they make subtle differences. So if you're looking first time around, you don't have to really worry about the model. If you're seeing things which don't seem to fit your experimental data, then you have to go back, look at the limitations of the model you're using, and see which one seems best suited to your situation. Same thing for repulsive forces. We have different electrostatic models, one from Darrell Velagrol's thesis, which Robert Flatt liked a lot. We have the classic Hogg-Healy-Fürstenau, which is early developed. Then we have a couple of simple approximations. Sometimes when you get into the details and you start presenting this work to physicists, they say, oh yes, but this model is too pragmatic, it's not accurate. Yeah? So we've inputted these models, again, the difference between each is relatively small, but it's more often than not to show to the non-believers that you don't really make a huge difference if you make something which is 5 times more sophisticated. Okay? We have only one simple steric model implemented at the moment. We haven't put in the Degen different systems. Generally, it's very difficult. It's difficult enough to estimate the adsorbed layer thickness, or to measure it. To get the idea of the different attachment density is something I think we can only approach through, if we're spectroscopically lucky, we have a molecule which has active groups, or by modeling. So we stick to a very simple semi-hard wall approach, which for pragmatic first-time calculations is totally sufficient. Yeah? It's a simple hard wall from Leonard Begstrom work. They can be easily added. Uli's done this in a modular fashion, so you can just contact him, and if you want to put something in, he'll explain how you can do it. So if you want to add a new steric model, you can do it. The parameters that can be modified, like I said, you have the name of the series, etc. The color of the plot, valence of the different, so we have the valence of the species in solution, we have the zeta potential, ionic concentration of our medium, we have the molecular volume of the solvent, which is normally water, then you don't have to change it. We have the volume fraction of polymer in the adsorbed layer. Like I said, these type of things, we generally leave fixed. You can vary them through the size of parameters that are generally accepted in the polymer literature, but they don't make a huge deal of difference. So the best thing is to leave phi, chi, alone. So this is the adsorbed layer thickness of our polymer layer. And then finally we have D, which is the plane of origin for electrostatic interaction. So if we have a simple system where we just do an electrostatic charging, we just use pH to change the charge on the surface, then we can take this as being more or less the surface of the particle plus or minus a water molecule. So we normally put in something like 0.1 nanometers. You can also think of it as being the where we measure the zeta potential, 0.5 nanometers. If you have an adsorbed polyelectrolyte which is charged, then it's a little bit more complicated. I mean, if it has a length of 5 nanometers, then it's not quite sure where we need to put the plane for the electrostatic interaction. Robert Flatt likes to put it at the edge of the adsorbed layer thickness. Jennifer Lewis likes to put it in the middle. Me and Leonard don't like to say where to put it. You do the calculations first and see what makes sense. So then there are a couple of things you can't modify, like the well is the absolute minimum on the curve, and the numerical points are following this program. There's also an estimation of the stability period. For that you need, this allows a calculation, like I said, for the formation of doublets. So you need the suspension concentration, the time you need it to be stable, 24 hours or 1 hour, particle medium density, and the required barrier is shown on the plot. So I'll run through just one little example before I go to the program. So Hamaker, a few weaknesses were particle sizes, temperature models, Hamaker constant stabilities, only one homogeneous system. So these are all presented on one graph. It wasn't so easy. So only a homogeneous system and only monodispersed systems. And as we've seen, even with the quasi-monodispersed systems of the silica this morning, when it's not really monodispersed, it's important. So Uli then improved the program with Hamaker 2. So all the parameters available for each, so you can complete freedom of plot presentation, so you can plot wherever you want. If there's a particular parameter that interests you, you can choose any. You can do 3D plots if you want to look at both charge and ionic concentration. And easy extension through plugins in the new model. And better plotting. So one little example, I was working with Ilford, and we were trying to make inkjet coatings. So inkjet paper, who never used an inkjet printer? Okay? So the paper normally had, in the past, a polymer layer to absorb the ink. Same stuff is used for babies' nappies, which is a fantastic absorption capacity. Can it absorb for Pampers for babies? Absorbs, 400 times its weight. But it was too slow. So we started looking at to see if we could do it with ceramics. We initially dispersed some gamma alumina with nitric acid, zeta potential 64 millivolts. We thought fantastic. Maximum volume fraction we could actually disperse was 10%. And this was too little to make a thick enough layer to absorb enough ink. So we want to make a porous layer that can absorb ink, and something that does it faster and more reliably than the polymeric material, which was too slow. Inkjet printers were 4 times faster than the polymeric layer, so the inkjet printer had to wait until it absorbed into the polymer layer. With acetic acid, we could get a 19% volume fraction, and this was sufficient to create a thick enough layer for the application. So we used our interparticle energy calculations to try and understand why. You can get this is now commercially available. It has this nanostructured layer on the surface that absorbs ink if you buy this Ilford paper. So we used this approach, like I said, we used the Beckstrom approach. So we looked at formic acid, butyric acid, propionic acid. We also compared the rheological results with our yield stress model. One of the things is when you look at all these diagrams I've been showing of this massive polymer, this is a 40 nanometer particle. This is the real size of formic acid compared to the particle. It's 80 times smaller. So you don't always need a very, very thick layer if the particle is small. So the Degussa C you already saw the other day, this relatively agglomerated powder, but we disperse it quite nicely. I mean, it only has an agglomeration factor of 2.2, 40 nanometers dispersed. We measured particle size distributions in the different acids. We don't see much, we don't see a great deal of difference. There's one little thing, is you see there's a tail of aggregates here, that creates a little bit of haziness. So you can see the sizes don't really change very much, all in the 40 nanometer range. If we look at now zeta potential, the ionic concentration changes. These are all 2% weight solutions, so the dissociation constant for these different acids change. We can see, in fact, as we go from nitric to formic to acidic, we decrease the zeta potential, but we're also decreasing the ionic concentration. If these are adsorbed as a simple molecule extended, this is the size we'd expect for our adsorbed layer thickness. So if we do a nitric acid, what we end up with is there's only 5 kT barrier, and there's deep primary minimum, so we wouldn't expect stability. With the formic acid, we close this deep minimum with our steric barrier, but we still have a small minimum. With acetic acid, we close the minimum totally, and because of this reduced ionic concentration, we extend the electrostatic interaction a long way out. So macroscopically, the nitric acid, it gels. After about 30 minutes, we make the dispersion, it gels, and we can't redisperse it. The formic acid gels, but we can redisperse it because we have this sort of small primary minimum. If we put it back into the ultrasonic bath, it disperses. We have something which has this shear thinning behavior, which wasn't what we wanted for this particular application. The acetic acid, no gelling, a 10% volume fraction or 10% weight fraction, we could disperse for 3 weeks. So you can see these type of calculations can help us understand how to disperse what we need on the surface to disperse our nano-sized particles. If you go back to the particle packing I was talking about on Wednesday, so if we see our electrostatic interaction starts kicking in a couple of kT at about 12 nanometers. So if we take an effective double layer thickness of 12.2, the volume fraction that's easily dispersed is about 19%. If you take into account this adsorbed layer thickness on the size distribution, so we have this double layer thickness. Like I said, because the particles are small, this is important. So we have an effective volume fraction, in fact, which is more like 65%. And from the log normal distribution model and Nolan and Cavana, the maximum you can do with this log normal distribution is 6.68. So you can see, although we only have 19.5%, because of the degree of agglomeration, the effective volume of agglomerates, and the double layer thickness, you have a high effective volume of these particles. And from infrared, we can see that, in fact, it was attached via the acetate group. So it's much simpler for molecules. If you have polymers, then the adsorb conformation is a little bit more difficult. So if you can use something simple to disperse your material, you just have to choose the right chemistry such that your molecule adsorbs on the surface. Theoretically, it's very simple. With these calculations, you can estimate what you need. The final microstructure looked a little bit like this. We have pore volumes with acetic acid of about 0.7 centimeters cube per gram. This is enough to adsorb the ink. So commercial films were produced using an aluminum oxide hydroxide because this small tail of agglomerates in the gamma alumina created a hazy structure. You have excellent quality. They're also water fast because the dye adsorbs strongly onto these. Another problem with the polymers is they weren't water fast. Production is done on sheets moving at 100 meters a minute. It's been commercially available for several years. So nanotechnology has been around for a while, but it all depends on dispersion. It took us 3 years to get to this point, and it's not something that's easily done. You have to give a bit of time. So I'm not going to go through all these applied examples. It's been used a couple of times in Nanoker by Marta Soares, by Miriam Miranda at the moment. We'll have a quick look at the effect of alumina on nanotech, which is something that Mirella Azar has been working on with Jérôme. So we have a size distribution. So you have 70 nanometer, 10% of the particles are less than 70 nanometers. The DV50, 50% less than, greater than 126. 90% of the particles are less than 155. So we measured at pH 4, we measured a zeta potential of 22 millivolts. And if we're in a background electrolyte of 10 to the minus 3 KNO3, I'll now try and so this is the program. I'm going to open. Now the problem is to find it. I quickly. Nanoker. Okay. Friday. Okay. Nanotech. Okay. So what you've got is you have a different model. So this is the interaction. So if we go for electrostatic, this is for the two DV50s, huh? So we have the DV50s. We have a look at the particle, yeah? So here we have the Hamaker constant for alumina, the density for gamma alumina, particle diameter, which is 126 nanometers, zeta potential 22. We put the zeta potential plane at 0.5 nanometers. Okay, so we can change these parameters. The medium, like I say, we're working in K on 3, 10 to the minus 3 moles, valence is 1, okay. And this is the green curve, okay. You can see we have a barrier which is really low. We have a relatively extended double layer, so you're gonna have a really funny viscosity, huh? It's not gonna be, it's gonna be strange, it's gonna be difficult to work with, huh? So, I mean, if you want, so if we go to the particle, we're now working with a green line. We say, okay, what do we need to do with charge? So if we can get it up to 50 millivolts zeta potential, boom, we have a massive barrier, huh? Okay, so if we go to the if we go to the medium, you say, okay, the problem is though we're working in very concentrated ionic medium, we're at 0.1, huh? Okay, in this particular case, we don't seem to have did I not tab out? Oh no, it's okay. So we don't have such a great effect. So it really depends on the system, huh? But if we, actually what we measured, huh? Then if we look at the difference between these two lines, so if we look at the DV90, so if you look at particle size, you can see that that's the purple line is for the DV90, DV50 interaction, so if you have two different particle sizes. The blue line is for the DV10, DV50 interaction, so you can see there's a different attractive potential depending on the size. Then if we look at adsorbed polyacrylic acid, and now we've got our steric barrier, our parameters. I mean, I've just said this is lying as a pancake, huh? As I showed earlier, we have a positive surface, negative polyacrylic acid. If we work at about pH 6, I mean, we need to move up the pH a little bit. When we adsorb polyacrylic acid, it ends up giving us a charge of about minus 40 millivolts. So we get charge and steric, and you can see there's just no attractive potential, huh? So you can really disperse your particles very well. So you can go to our website, you can download it, you can play with it. And if you find anything you're not happy with, you can get in touch with us, huh? So that brings me to the end. Lots of people to thank, particularly Uli Aschauer. I've been dreaming of an easy-to-use program. We've been doing these calculations for about 10 years, where everybody was making their own little program, their own Excel sheet, which even I had problems following. And if there was a mistake, you couldn't quite follow it. This is something which is really easy to use. And if you're working with nanoparticles, I really, really encourage you to go and use it. Get an idea of what you need before you start. Huh? So, and I'd like to thank you for your attention. Thank you.
Good afternoon, ladies and gentlemen. We are going to start the last session of this training action. I pass the floor to Christopher Lilot, on the IP project manager of IP Nanoker.
Thank you very much, Mr. Damborenea. Ladies and gentlemen, dear colleagues, let me start with some data about the training action we are closing this afternoon. Last year we received nearly 300 applications from all parts of the world. Due to the fact that we are obtaining European co-financing, we only accept candidates coming from European countries. At the end of the selection process, 150 persons have been chosen who were invited to this event. 75 female and 75 male participants, 75 participants between 20 and 30 years, 57 between 31 and 40 years, and 17 between 41 and 50 years. One participant is 52 as I. 46 participants are Spanish, 12 are Portuguese, 11 are Polish, 9 British, 7 German, and other are French. In total, 33 countries are represented here in this training action. Finally, we invited 143 persons, which then decided to travel to Madrid. After this week of intensive training about actual research on future applications of ceramic nanocomposites, Ramon Torresillas, Adrian Alonso, and myself would like to thank to all of you for your attention, for your questions, and for your comments. We hope you enjoyed this training and can take advantage of it during your professional career as scientists or engineers in research organizations, universities, or companies that look for new knowledge-based materials and their use in high-value products and processes. I'd like to express my special acknowledgements to the responsibles of the different training modules, Dr. Giovanni Baldi, Dr. Frank Kern, Professor Gilbert Fantozzi, Professor Paul Bowen, and Professor Ramon Torresillas for the definition and selection of the topics and the invitation of the speakers. I would like to thank also to my institution, to the National Spanish Research Council, CSIC, for the organizational support and the presence in the opening and also in the closure of this event, and for giving us as IP project consortium and as collaborators of the Nanomaterials and Nanotechnology Research Center in Asturias the opportunity to celebrate our training action in this imposing conference hall in Madrid. Once again, many thanks for all your cooperation and participation. I wish you a good trip back home and say goodbye. Thank you.
Well, ladies and gentlemen, dear colleagues and friends, I'm going just to say a few words because I know you are very tired after these very intensive sessions. You start very early in the morning, you finish very late in the evening, and then I am sure you are very tired. But till 9 o'clock you have the cocktail. Just let me say just a few words. First of all, it's on behalf of our president, Rafael Rodrigo, and all his team. Well, I would like to say that it has been a real pleasure to be here and to host you during all these days, to all the participants, to the European Training Action on Ceramic and Nanocomposites. And just for me, there are 3 reasons that make me especially happy to be here at this moment. The first one is because it ends as a successful action with a record of participants, as Christopher said now, countries and scientific representations of very, very high level. The second, and which is very important also for CSIC and for all of us, it has been an example of collaboration and interactive dialogue between scientists from academia and scientists from the industry that in some way that can show the real way to policymakers and representatives of national and European funding institutions on this field. As it could be seen during these days, along these days, the funds the project has spent are really well spent, and I have to congratulate on them. And the third reason that made me happy to be here is a personal reason, is because I am a material scientist. And I am involved in corrosion research, which is a very close area of research to this action training. And then I'm really feel at home just here, and I am surrounded by colleagues and friends talking the same language. Well, as our vice president told you the first day, Carmen Peláez, we are organized into 8 science and technological areas covering all fields of knowledge, from basic research through to advanced technological development, We have at the CSIC 128 institutes, covers from social science and humanities to to science and the technology of food. And then we have a very broad vision of science at this moment. From this number of institutes, 75 are belonging to the CSIC, and 53 are with the university. Well, one of these 8 areas is the material science and technology, is deeply involved in the scope of this training action, and at least 3 institutes is research on nanomaterials and nanotechnology, material science, and ceramic and glass have participated in the conference and in the project. In our action plan 2006-2009, which is finishing now, CSIC launched a specific axis on nanotechnology and nanoscience, and creating new institutes from exciting research groups and with links to exciting centers and institutes, with the objective of promoting top quality research and encouraging knowledge transfer to the productive sectors. Other objectives were to train researchers and to be present at international level. All these aspects have been widely reached with the present IP Nanoker. High scientific contributions on the design and functionalization of ceramic nanocomposites and ceramic material solutions which permit to the industry the application of this kind of materials. Well, just in closing, I would like to express my gratitude to Christopher and the organizers, and in the name of Christopher and Ramon, and to our scientists also, the people who is here and of CSIC, for their big contribution and continuous effort to make research internationally recognized. Well, you know, until 9 o'clock you have the cocktail dinner, you have time, and then let me do just a few recommendations. It's just surrounded CSIC. You have 2 large facilities managed by CSIC, which are very impressive in Madrid. One is the Royal Botanic Garden, which is wall-to-wall to the Prado Museum, belonging to CSIC, and it's a very nice afternoon to have a walk through the gardens and to see what another kind of scientists are doing in this sense. And if not, just on the back of this building is the National Museum of Natural Science, which belongs to the CSIC also, and it's a good opportunity. Now you have to take a rest and to see another things. And well, just finish, dear colleagues, one more. Let me extend a warm and heartily see you soon to everyone, and I thank you.